Hello everyone, welcome to Chapter 4, Applications of Derivatives. We look at applied optimization. As the name says, it's about application, so we'll apply derivatives to optimize problems that require either a maximum area or a minimum height and things like that, where derivatives would help us to solve those problems. So we'll look at different problem types and see how we can use the idea of derivatives. An open top box is to be made by cutting small congruent squares from the corners of a 12-inch by 12-inch sheet of tin and bending up the sides. How large should the squares cut from the corners be to make the box hold as much as possible? Okay, let's think about this. An open top box. So this is a box with no top, so it doesn't close. That is to be made by cutting off squares from a 12-inch by 12-inch sheet of tin. So I can think of 12-inch by 12-inch means that we're talking about a square sheet, right? And we are cutting off squares in the corners. And they're congruent squares, which means it's an equal size that will be cut off. It's a 12-inch by 12-inch, so we will have equal squares, congruent, right? So equal squares, same squares that will be cut off at each corner. Now that the corners are gone, we'll bend up the sides, and so that makes that box. So you see the box is a 3D figure because you can, hold something in it. And so the question is, how big should these squares be cut so that we can make the box hold as much as possible? So to maximize the capacity of the box. I have these better diagrams here to depict this situation. Now remember, we are cutting off the sides, which means it's a square, so this will be x. Each side is an x, and because they are congruent, each of them will be x, right? So if this whole side of this tin sheet is 12, you're cutting off x from here and x from here. So you're taking away 2x of this side, and you're doing that to every side because it's a square. Okay, that's what is depicted here. Okay, this is after the squares were cut off. So when you bend up the sides, you get this box. And so the sides of the box, after bending them up, would be 12 minus 2x, because you took away an x from one corner and from the other corner. And that's going to be true on all four sides. That's what is shown here. All right, now the question was, how large should the squares be cut from the corners to make the box hold as much as possible? So the box hold as much as possible is a language to indicate volume. So we use the volume formula. Volume is length times width times height, because this is a 3D figure. We have the length and the width to be the same because it was a square tin, but the height would be how high it is bent up, because we bent the sides. The bent sides would be a height of x, as you can see, because that was the edge that was cut off. So the length will be 12 minus 2x. The width will be 12 minus 2x, and the height will be an x. So you can pull out a 2 from here and a 2 from here. That will make it 4, and bring this x in the front. So that will make it 6 minus x times 6 minus x. You can FOIL this. Let me write that again. Okay, so combine all the like terms and everything, and when you finally distribute this 4x inside, you would get this expression. So we got this expression completely in x, so you can rewrite this volume as v of x. Okay. All right, now we know the volume means that the capacity, what it holds. So volume should always be positive, right? You can't have negative capacity. So v of x must always be greater than or equal to 0. So we expanded this, but when we want to use it in an equation format, I'd like to keep it in this factorized form. So I have 4x times 6 minus x times 6 minus x greater than or equal to 0. What this does for me is well, we can rewrite this as 4x times 6 minus x the whole square greater than or equal to 0. So by setting each factor to be greater than or equal to 0, I get 4x greater than or equal to 0 and 6 minus x the whole square greater than or equal to 0, which simply means x is either greater than or equal to 0 or 6 minus x is greater than or equal to 0. Take the square root on both sides, you get that. And then you basically get 6 is greater than or equal to x. So if I'd like to, if I were to put this all in the way we have the x on the left, if I had x on the left, it will be x less than or equal to 6. So technically we're saying, well, the volume will be positive provided the x, the side of the square that you're cutting off, should be definitely positive, right? You can't have a negative side. That must be positive. But you can't go any more than 6. Because if you went more than 6, what happens? You'll be cutting off the entire tin. There'll be no capacity. There'll be nothing there. So we now know that your x that you're going to cut off should belong to this interval 0 to 6. Yeah, this is the domain for the volume. That makes perfect sense. Okay. Now, I want to recall v of x. The expanded form, 144x minus 48x squared plus 4x cubed. Now that, if I took the derivative, because I need to find the critical points to know where it is maximum or minimum. Remember, local max, local min. So we want to find, let me write that here, to find maximum volume. We need to find where we need to find the local max or absolute max, anything, right? Because we want, especially in this domain, we want to find the absolute max. And so we need to, this implies we must find critical points. That's what we did in the previous lectures. Implies dv over dx must be equal to 0. So take the derivative of v. That will be 144 minus 48 times 2 will be 96x plus 12x squared. And this has to be set to 0. To pull out all that's common, 12 is common here, so 12 minus 8x plus x squared equals 0. You can always rearrange this so it's easier for you to see it in the quadratic form. Factorize this, of course. X minus 2 times x minus 6, 0. Now set each factor to 0. So we get x equals 2 and x equals 6. These are our critical points. Okay. Critical points, x equals 2 and 6. And the endpoints, you remember that? Endpoints of your closed interval. In this case, our closed interval was from 0 to 6. That became our domain, right? But we do know that this 0 and the 6, these are the endpoints where you really can't cut your square at these endpoints, because 0 means you didn't really cut out any square, 6 means you really cut out the entire tin. So 2 is the only interior point. Okay. So then we come back and we say, okay, if we were to evaluate at the endpoints, we already know that the volume will be 0. But if we evaluated the volume at this interior point 2, we can then plug that in 144x. So x times 2 minus 48 times 2 squared plus 4 times 2 cubed. Evaluate this and you get 128. Because these were all measured in inches, this is volume, so it's either inch cubed or cubic inches. That's how you do. This is where we have the maximum volume, isn't it? That is the whole idea of absolute max. Absolute max is where the volume is maximum, and it occurs at 2, which means the squares must be 2 inches each side for it to be cut out. So we can come back and conclude the answer and say this implies, because the question was how large should the squares be cut from the corners. They didn't ask about the volume, they said how large should the squares be cut. So we come back and say we were able to get the maximum volume for x equals 2, so the cut out squares must be 2 inches on each side. And that's the end of this problem. So you'll find that it's really interesting because it's meaningful, but it also helps you to really apply derivatives, the idea of derivatives and the critical points and the endpoints to understand what that local or absolute maximum, like in this case, means. You have been asked to design a 1-liter can shaped like a right circular cylinder. What dimensions will use the least material? And here's the shape of the can. So think of a soda can, right? Now the question is, how should we build this can so that it will use the least material? So should it be like this, the way it's shown, or should it be even more flatter, therefore shorter and wider, or should it be tall and thin? So which will give us which dimension? Meaning, when they say dimension, you're trying to measure the in this case, the radius and the height of the cylinder. So for that, first we need to understand that when we talk about a 1-liter can, 1 liter, that information there actually refers to the volume, because that's the capacity of it. So when we're talking about the volume, then we need to consider the volume of this can. So volume of the can for a cylinder is pi r squared h, okay, where r is the radius, and here we have 1 liter. Okay. So what I'm going to do is consider this radius in centimeters, because we need to convert this to liters. And what we understand is 1 liter is 1000 centimeters. So if we measure them in centimeters, then the square and this h, right, their dimensions will give us the cube. So that centimeter cubed, 1000 centimeter cubed will be 1 liter. Height in centimeters. So what we do now have is that this volume is 1 liter. We know that 1 liter is 1000 centimeters. Okay. So then you can set this as 1000 centimeter cubed, cubic centimeter. All right, so we got that. That's your volume. That's what is given to us. However, they're saying what dimensions will use the least material. When they talk about least material, then you're not talking about the volume, what it contains. It's about the outer covering, right? It's what the material is used to build this cylinder. So that means we are talking about the surface area, right? The surface area that goes around on the top and the bottom. So surface area of the can, cylindrical can, is you need to consider the surface area on the top and the bottom, which are circles basically, and then the surface area of your the cylindrical part. So now we have 2 pi r squared. Pi r squared is for the area of a circle, because we have 2 circles, one on the top, one at the bottom. It's 2 pi r squared plus 2 pi r h. You can do a quick search or reference into the algebra books to recall the surface area of a cylinder. Okay, now we're asked to find the least material. Least material implies that we're looking for the smallest possible total surface area. That makes sense, isn't it? So in order to help us to focus on surface area, we're going to use the volume of the can within it. And I'll tell you why. It's similar to one of the problems we did earlier with related rates, where we wanted to create an equation with one variable. If we had two variables, then we had to rewrite one of the variables in terms of the other. So right here you have surface area equation containing R and the H. There are two variables here. So we could use the volume information to help us replace one of the variables so that we get them all in terms of preferably radius, all in terms of R. Okay. So let's do that. To rewrite H in terms of R, we take the pi r squared H, the volume formula, which was equal to 1000 centimeter cubed, and solve for H, which means you divide both sides by pi r squared, so that gives us 1000 over pi r squared. And this is good enough for us to take it back to the surface area formula. Surface area of a can is 2 pi r squared plus 2 pi r h, and in the place of h you're going to plug in what you just figured as 1000 over pi r squared. If we clean this up, if we simplified this, 2 pi r squared plus the pi's cancel off, the r, one of the r's will cancel off, and that leaves us with 2000 over r. So this is the surface area formula, and we need to find the appropriate r, because that's the only dimension that's going to adjust it for us, because we can use r and indirectly know what h should be to know what least material to use. So what we begin to identify is that you have two terms. The first term you have r in the numerator, and second term you have r in the denominator. So this term, right, this term will dominate when r is large, isn't it? When r is large, then this fraction will become really small. So this is the term that will dominate. And when this term dominates, the shape will be, remember your radius is really large. So let me take you back to this diagram here. This is your radius, isn't it? This radius is really large. If you want your radius to be larger than what is indicated here, then you can't have the height of your can to be the same. The height has to reduce because you can only accommodate 1 liter in this can. So you can't have it as tall and still have a radius that's larger than what is here. So that means your can has to get really short. So then we get the shape to be short and wide. And to depict it, it's going to look more like this. It's still a cylinder, but the shape has kind of significantly shortened and it's gotten wider. Now, on the other hand, we know that this term will dominate. This term dominates when r is small. That makes sense, isn't it? When r is small, this fraction gets really large, and so that becomes that dominates this 2 pi r squared. And therefore, the shape, when r is small, okay, let's go back here. You want to make this smaller than what is here. If this becomes smaller, if radius becomes smaller, you need to compensate for it in the height, so that you need to make your can tall. It should be tall in order to accommodate a smaller radius. So if you come down here, the shape will then be tall and thin. So you're going to get this really skinny can. And we've seen cans like that too, right? Both these types. So we just want to know which one would be better for us, not for capacity of the cans, but for the least material. Therefore, our focus is not on the volume, our focus is on the surface area to use the least material to make these cans. Alright, so what we see then is surface area formula, what we got here, is all positive, right? Because we know that radius R has to be positive. That can't be negative. So that much we know. I'm trying to find the domain, like how we found the domain for the previous problem. So I know the radius has to be 0, so we start with R at 0. But what is the highest, or what's the end point? So we're trying to find the closed interval here. What's the end point? So considering the end point here, there is no end point for R, literally. I mean, at least mathematically. I'm sure there is an end point, but mathematically, there is no end point for R. This graph kind of illustrates it for us. Okay, we want to find a radius, right, that will minimize the surface area. But when we graph this equation here, right, the surface area equation, 2 pi r squared plus 2000 over r, if you graph that, you see that it's basically concave up everywhere, isn't it? Yeah. So it is, it's basically positive everywhere. So the radius is actually has no endpoint. All we can see is that if the radius is small, it's tall and thin. If the radius is large, it's short and wide. But because of the turn here it makes, right, there will be an absolute minimum. And that is what we want to find. Absolute minimum will give us the minimum or the least material we need for the surface area. So it is that absolute minimum that we can find. Therefore, we don't have to worry about the endpoints, literally, because there is no endpoint for R to find the absolute minimum. We do need the critical points and the endpoints. Because we know that there will be this absolute minimum, these endpoints don't matter. So we'll go after the critical value, the interior point. So for that, it implies that we have to take the derivative of SA, right, surface area, over derivative of R with respect to the radius. So then we have this equation here, so I'll just use that. That will be 4 pi r. Remember, it's only the r, so pi is a constant. So it's going to be 2 pi times 2r. Plus r is in the bottom, so take it to the top. Okay. So that's going to be actually minus. It will be r power negative 1. So minus 2000 over r squared. Take the derivative, please. I'm going to quickly rewrite this as 2 pi r squared plus 2000 r power negative 1. Okay, so that is how you get this. Now I set this equal to 0 to find the critical points. So take the LCD here. Oh, so that's going to be pi r cubed then. So clean this up, so we get 4 pi r cubed minus 2000 equals 0. R cubed will be 2000 over 4 pi, just 500 over pi. We want r, not r cubed, so take the cube root of this. So cube root of 500 over pi. If you use your calculator, this value comes out to be approximately 5.42. We assumed r to be measured in centimeters, so if you want, you can write that in centimeters as well. Okay. So this is a critical value, right? And it's definitely the interior. But here, because we don't have an endpoint, we're not really worried about the interior. We got a view of the graph. So we know this is the minimum value. The interior value should give us the absolute minimum. Okay. This implies that when r equals cube root of 500 over pi, the value of the surface area is an absolute minimum. Now we need to find the dimension. So we figured out where it's happening. We need to figure out the dimension. So we already got r. The other dimension in this surface area information is the h. And if you go back to h, we solved h in terms of r, isn't it? So we said h is 1000 over pi r squared. So I'm going to put that here. And now we got the r value. So that's going to be cube root of 500 over pi. That's your r. You're going to square that. Pi r squared. So I don't write this as, well, you can use the calculator at this point, but I'm trying to see, trying to show you something else. So I'm going to split up this 1000 as 2 times 500 over pi, right? And this one here in the bottom is 500 over pi power 2 over 3. Can we write that way? Oh, certainly. So we got that. So 2 times 500 over pi times 500 over pi, which is sitting in the denominator, this one. If I move it up, it becomes negative 2 over 3. Isn't it? So that means this one has the power 1. Combine the powers, add the powers. So that will be 1 minus 2 over 3. That's going to be 2 times 500 over pi power 1 over 3. So h is 2 times cube root of 500 over pi, isn't it? But what is cube root of 500 over pi? That is nothing but your r, isn't it? We found r to be cube root of 500 over pi. So if you come back here, this means it's the same as 2 times r. So why I did this was to bring this relation between h and r, where we're saying h is 2 times r. Okay, so you will get to use least material if your height was twice the radius. Doesn't matter what the radius is. If your whatever the radius is, 2 times that radius, if that becomes your height, then you can use a 1 liter can that uses the least material. So this is why I brought this down. But if you were to get this numerically, you know, just the value right here, oops, I can simplify this using the calculator, and that comes out to be 10.84. Okay, so you can also verify that by seeing that h is 10.84 and r is 5.42. And so I'll just write centimeters. 5.42 times 2 is 10.84. So you can see right there, even in the approximated version, they match this relation. So what we're saying is this 1 liter, let's just say the 1 liter can that uses the least material has height equal to twice the radius and here h is approximately again 10.84 centimeters and radius is 5.42 centimeters. Now I'd like to consider examples from economics. So for that, I want to kind of create this background. In economics, we usually have three things: the cost, the revenue, and the profit, right? So there are many other things, of course, but we are focusing on these. So R of X is the revenue from selling X items. And then we have C of X, which refers to the cost of producing X items. And P of X, as you must have guessed, is the profit, will be the revenue minus the cost, right? Profit from producing and selling X items. So if we took the derivatives of these, okay, R prime of X, we call it the derivative in math, but economists use the terms like this. They call it marginal. So it will be marginal revenue, C prime of X, the first derivative of cost, will be called the marginal cost. And P prime of X will be the marginal profit. So why do we need to take the derivatives? Now what happens is the profit P of X, right, which is R of X minus C of X, this profit function has a maximum value. And that's desirable, isn't it? We want your profit to be maximum. This has a maximum value at the critical point of P of X. Agreed? Isn't it? That's where you have the maximum value, absolute maximum, absolute minimum. So in this case, profit. So it will be the maximum value at the critical point. So if it's a critical point is found by taking the first derivative and setting it equal to 0, isn't it? That means you take the derivative. So R prime of X minus C prime of X will be equal to 0, which implies that R prime of X is the same as C prime of X. In other words, the marginal revenue and the marginal cost are the same. Their slopes are the same, basically, right? The slopes. So if you're looking at it mathematically, the derivative of one and the derivative of the other are the same, which means if you draw their tangent lines, the tangent lines will be parallel to each other because their slopes are the same. We discussed this in a previous lesson. So that is the idea that we're using from math and applying it in economics, where we say, the marginal, when the marginal revenue and the marginal cost are equal, that is the place where we find the maximum value for the profit. So in economics language, this is how they explain it. It says, at a production level, yielding maximum profit, look at the language, okay? The production level yielding maximum profit, marginal revenue equals marginal cost. And I'd like to kind of depict this using a graph so we can really see what's happening and why it causes this. So here's the graph. We have the blue graph, right? This blue one, it's called the cost C of X, and the yellow graph is your revenue R of X. So we have let's focus on the blue graph, the cost function. The cost function seems to be concave down in the beginning. It starts off as concave down, and then after this point B, it becomes concave up. And then if you looked at the yellow function, it begins as concave up, and then after the point B, it becomes concave down. So that is, all this is in mathematical terms, isn't it? So what happens is, when we have this point B is the place where the blue and the yellow graphs meet for the first time, because they also meet again the second time. So this is where they meet the first time. And that's called the break-even point, where the revenue and the cost are meeting. So what happens is, to the left of B, what happens is clearly the cost is more than your revenue. The blue graph is higher than the yellow graph. So the cost is more, which means that you have less profit. So the company operates at a loss, technically. And we know that when you can find a point where the tangent line, when you draw the tangent line that passes through that point on the blue and on the yellow, and these two tangent lines are parallel to each other, then their slopes will be the same, isn't it? And that is where you have the local maximum for loss, and that is written here to us as minimum profit, where C prime of x equals R prime of x. So that's happening there, okay, to the left of this break-even point. To the right of the break-even point, we see that the yellow overtakes. The yellow is higher than the blue, which means the revenue is more than the cost. Therefore, we have the company operates at a profit. And when that happens, once again, if we can find a point, and these are points found through the critical point. So if we can find this point where the slope of the tangent line through the point on yellow and the slope of the tangent line through the point on blue are the same, that means these two lines are parallel. These two tangent lines are parallel to each other. And that is the place where you'll have a maximum profit, because you can have absolute maximum or absolute minimum. And so we found both of them happening, one to the left of B and one to the right of B. To the left of B is a minimum, and to the right of B is a maximum. And so that is what they indicate to us. Now, if you see this point here, where they meet again for the second time, this is a place where, once again, the cost after that overtakes and the profit, the revenue goes lower. So to the right, we see that the cost exceeds the revenue, and this could be due to many reasons, because of rising labor, material cost, even market saturation could contribute to that. So what happens is, after this point, the profit obviously suffers, and therefore the production levels become unprofitable again. Okay. So I'll say after this point, production levels are unprofitable. It was so before B, right? Even there the production levels were unprofitable. But you see that ideal space is between this B and the next time they meet. That is where you maximize your profit. So you need to endure until you reach that break-even point. After that, you'll experience profit. But if you go on the same way, after a point there again, you'll become unprofitable. That's the reason why you see this language at a production level yielding maximum profit, which is between this B and the next point. That's the production level you want to maintain, because that is your X here, right? Items produced. At that, in that stage, if you want to get the maximum profit, that will happen when your marginal revenue and your marginal cost are the same. Here is a problem related to that. Suppose that R of x is 9x and C of x is x cubed minus 6x squared plus 15x, where x represents millions of MP3 players produced. Is there a production level that maximizes profit? If so, what is it? I like this problem because it conveniently gives us R of x equation and a C of x. Okay, we now know, and let me also write here, x is millions of MP3 players. It's measured in millions. So we know that we have the break-even will occur when R and C meet, isn't it? So that means C of x will be the same as R of X. That's where they meet. And we know that maximum profit will occur when the marginal cost and the marginal revenue are the same. So we have these two things. So let's begin off with finding, the focus is on, where are we? Maximizing profit, right? Maximum profit. So we need to get the C prime and the R prime. So I'll get R prime of X is 9 and C prime of X is 3x squared minus 12x plus 15. So we got these two. So maximum profit can be found by setting these two equal to each other. You know, it's a quadratic equation, so make sure that you bring them all to one side of the equation. So subtract 9 on both sides, you get plus 6 equals 0. And you can use quadratic formula for this. Do you remember the quadratic formula? X equals negative b plus or minus square root of b squared minus 4ac all over 2a. So use that information, and I will let you complete that part because this is just complete algebra. So I'll say after some algebra, we get x to be 12 plus root 72 all over 6. You get 2 of these values, right? Or 12 minus root 72 over 6, plus or minus. You can simplify it further in the radical form, but because it's a word problem, you know, you can go for the decimal answers as well. This reduces to 2 plus root 2. This will be 2 minus root 2. And this value would come out to be 3.414. And this one would be 0.586. These are your x's, but come back here. X represents millions of MP3 players. So if it looks like really small numbers, it's because it's in millions. Okay. All right. So these because we set our derivative to 0, and of course use the quadratic formula for this. This means that these are the critical points. Now our first derivative test, right? That helped us to even our EVT. EVT said if f is continuous and you know, on a closed interval, then we have both absolute max and absolute minimum. But we don't have a closed interval here because we know that x has to be positive. But what is the maximum number of MP3 players that can be produced? So theoretically, we can go on producing them, right? At one point, the equipment will break. But theoretically, we can go on producing. So there is no end point there. So is there a way to handle this? Then what we can do is look for other tests. Remember, we looked at first derivative test, EVT, first derivative theorem, mean value theorem, second derivative test for concavity, second derivative test for local extrema. So you have all these other tests that you can continue to use to locate your maximum minimum. Here, our question is what maximizes? What is the production level that maximizes profit? So for that, we need to, we can go ahead and use the second derivative test, both for concavity and for local extrema, to understand the shape or the graph for this. Okay. So if I did the second derivative, r double prime of x, r double prime of x would be 0, right? Because derivative of 9 is 0. Then c double prime of x will be 6x minus 12. So let me write that out here. X minus 12. So this implies P double prime of x will be R double prime of x minus C double prime of x. Okay. Because the second derivative test tells us that when the first derivative is 0 for a particular point, and if you could find the second derivative to be negative for that particular point, then you know there is a local max, and if it's the other way around, it's a local min. But if it is equal to 0, then the test fails. So I'm calling upon the second derivative test, and let's see what happens. So that's going to be, what is this? 0 minus 6x minus 12. So that's basically 12 minus 6x, right? Distribute the minus. So what we see then is P double prime of x will be positive when x is, try plugging in different values. So basically what we're trying to do is, you have these critical points, right? So these are the critical points. We do know it has to be 0 or more. It can't be negatively producing items. So it has to be, so between 0 and 0.586, choose a test point and plug that in, okay, and see what happens. Okay, so that's what we're going to do here. Maybe I'll just do that number line here, so it's easier for us to see. So 0, 0.586, 3.414. So that comes from the first derivative, okay. Yeah. Then I want to set my second derivative to 0. So what does that give us? That gives us 12 minus 12 equals 6x, so x equals 2. Okay. So I'm going to bring that here as well. There is a 2. Okay. So the focus here is in finding the sign of P double prime, okay, second derivative. So if you look at the sign of P double prime here, so take a test point and plug it in P double prime basically, okay. So you can choose 0.5 and plug that in here. 0.5 is a half, right? So plug that in and see what you get. Positive. And in this interval, you could probably plug in 1, right? So that will be positive. Between 2 and 3.4, so go for 3 maybe. And because right here, when you plug in for 3, 6 times 3 is 18, so 12 minus 18 is negative. Anything more than that, that also gives us negative. Yeah. So what we know from these tests is when we are looking at the second derivative to be negative, okay, that means that's where you have a local max, and we want to focus on maximum profit, and therefore we will use the one that has the negative, okay, second derivative to be negative. So this is negative, and this is negative in these intervals. Okay. So you know that at this point particularly, we have a local max, isn't it? So because of that, the local max, we can now come back and say the maximum profit occurs at x equals 3.414. Okay, this is the point where the revenue exceeds the cost. Okay. And we know that the maximum loss occurs at x equals 0.586, the other point, because this is where the cost exceeds the revenue. Okay, so then we want to know what that maximum profit is. So go ahead. In fact, P of x. So in your P, in the place of x, you plug in 0.586, and that was. We'll go back to the equation. Hold on. Just before that, I want to write P of x, which is R of x minus C of x, right? Because I don't think we wrote that information. So R of x minus C of x, R of x is 9x minus C of x was x cubed minus 6x squared plus 15x. Again, clean up all of that, and what we get is negative x cubed, and put them in order, of course, with the highest power, starting with the highest power. So that plus 6x squared minus 6x. This is what we have. Okay. Now we can find the profit. So the maximum loss is estimated to be at 0.586. Let's go ahead and check that out. Let's see if that's the case. Of course, use your calculator. And this answer computes out to be negative 1.65653. And let's do 3.414. And here we expect maximum profit. So we have that, and then we have to plug in these values, and that answer comes out to be 9.6568. Okay. If you did the concavity, you will also know if this is just a local max or if it's the absolute max. So we know that this is going to be absolute max. And we can kind of verify that by checking the concavity. That way you know if it is where is concave up, where is concave down. For that matter, if you took the second derivative, right? Second derivative of 0.586, that value, plug that in. That gives you a positive value from second derivative test. SDT, I'd say, second derivative test. It means that it's concave up. Maximum. And then the second derivative at 3.414 gave us concave down. And there we expected a minimum. Okay, so we have all these things that help us to line up. So we know that the maximum profit is given by this value here, and we have that profit, maximum profit, occurring at 3.414. Owners of a bike rental company that charges customers between $5 and $25 per day have determined that the number of bikes rented per day, N, can be modeled by the linear function N of P as 150 minus 6P, where P is the daily rental charge. How much should the company charge each customer per day to maximize revenue? Not as straightforward as the other question where they gave us the cost and the R of x and C of x, that problem. So here we have to build it ourselves. So let's go ahead with the R. You know, R is the revenue, right? And here it's not R of x, it's all related, it's related to P. Okay. So R of P will be the revenue Now we have this revenue will be the same as, what is the income? The income is the number of bikes rented, right, times what they charge per bike. So I'll say number of bikes rented times price charged per day per bike, or per bike, charge per bike per day. That makes sense, isn't it? Because P refers to the daily rental charge. So we're talking about the daily ones. Okay. Now that means the number of bikes rented is represented by, you can see that here, it says N, right? So that is N times the price charged per bike. Price will be the daily rental charge, which will be P, N times P. But we're already told that N is 150 minus 6P. So 150 minus 6P will be N times P. So that will be 150P minus 6P squared. So R of P is 150P minus 6P squared. Now the company wants to charge the customers between $5 and $25, right? So it's as if now we have the revenue, the domain is between 5 and 25, because they will charge between 5 and 25. So you have basically a closed and bounded interval here. Okay, so your R is continuous on this, and it's continuous because you got your R function to be a quadratic function. So it is continuous and closed interval here. Right away, you know that EVT kicks in, extreme value theorem, because that's all it needed. It needs the function to be continuous and on a closed interval. That means it guarantees that we will have an absolute max and absolute min in that interval. So our job is to choose which one we want. We want to find the maximum value, right? Because the maximum revenue is what they want us to find. So this implies maximum revenue implies critical points. Because critical points will give us the revenue, and of course we have to check at the endpoint, so we're going to do all that. So R prime of P will be 150 minus 12P, right? And then set that equal to 0, and from this we get P equals 12.5. So 12.5 is an interior value. Clearly it is in the interval 5 to 25. So let's now evaluate. I'll just write here, evaluate R of P at these the endpoints 5 and 25, and the critical point, which is the interior of the interval. I'm sorry, I said R equals, it should be P equals. P equals 5 and 25, and P equals 12.5. Okay, so then let's plug that in. R of 5, R of 25, and R of 12.5. We need to know where we get the maximum value. So plug that in your R function. Okay, so when I plug this R of 5, I get 600. When I plug in R of 25, I get 0. Okay, so let me take you back quickly. I'm asking you to plug that in here. 150p minus 6p squared. If it helps, I'll just write that here. And 6p squared. And that comes out to be 600. And then this is 150 times 25 minus 6 times 25 squared. That is a 0. And lastly, That comes out to be 937.5. So among these three, we clearly see that this one gives us the maximum value. So we can come back and say this implies the maximum revenue occurs at P equals 12.5. So the company should charge $12.50 per day to maximize revenue. Okay. So we looked at these problems where we used different tests. So in this one we used EVT because we were able to get the endpoints and prove that it was a continuous function on that closed interval. When we couldn't find the endpoints, then we used a second derivative test to check concavity, because concavity, if it's concave, let's say concave up everywhere, then you'll have an absolute minimum. If it's concave down everywhere, then you'll get an absolute maximum. So it gives you extra information so that you know that it's happening in the interior and you don't have to worry about the endpoints. So that is the exercise here, that each problem is very different from the other in that the context is also different as well as the approach is also different. But the underlying fact is that we will be using one or more of those tests. We've seen before in the previous lectures that we saw theoretically we're going to apply them in this applied optimization problem. I hope you'll have a good time exploring these different problems, and I hope it improves our critical thinking. So I will see you in the next video.